My name is Dmitry Petrashko. I'm student of Martin Odersky, working under his supervision. And I'm here to present you one of the new parts of ecosystem of Dotty. So, yeah, you can find me on GitHub. I'm DarkDemius everywhere. Before this, I have been working on macro-generated collections for Scala, which were substantially faster than the current both standard and parallel collections. And while doing on this, I understood that there's a lot to be improved about both memory layout and performance of Scala-generated bytecode. So in order to implement it not only for collections, but for arbitrary Scala code, I've joined Martin in effort in building the new compiler, Dotty. And we've succeeded in building it, I would say. And since Dotty Bootstrapped, I have been working on making the optimizer part of Dotty, which is Dotty Linker. And I'm also supervising new students who now work on Dotty. So to say that I worked on Dotty, you can have a look at this graph where you can see that more or less if you have a bug in Dotty, the likelihood of me introducing this bug is as high, a bit bigger than the likelihood of Martin introducing this bug. So I'm also the person likely to fix it. Yeah. Okay, so this talk will be about how to build fast Scala code, how to compile Scala into fast code. And in order to understand what's fast code, we need to first understand why there is a possibility for improvement, why Scala can be faster, what makes Scala slower now. So there are two reasons for it to be slow in every particular application. The slowness can either come from the library, which is inefficient, or from the user code, which misuses the library and uses the efficient library in inefficient ways. I will cover both of these topics during my talk. So, okay, I'll start with the library as a source of slowdown. So, if we consider these two examples of code, one written in Java and the other written in Scala, the Scala one is a lot easier to follow. It's clear what it does. I like this code a lot more. Java is quite verbose. You need to write an explicit cycle, and you spend more time writing it and potentially introduce more bugs by writing it wrong. But unfortunately, the Java code runs faster. And the reason here is actually in the Scala collections library, the source of slowdown. So why does it run slower? Let's compare what does Java do here and what does Scala code do here. In case of Java, you have the range check here. So for every iteration of cycle, you're checking if you need to do the next iteration of cycle. You're actually going to do the addition that we're looking for. And then you'll do the index increment. So you're doing 3 operations per every iteration of a cycle, and all of those operations are really fast. Compare this with Scala, where actually the reduce function itself is implemented in terms of for each. And it creates a lambda to be passed there. So similarly to Java, well, we're doing a range. We're doing a summation of a collection here. We need to do a range check here. Then, because we're being abstract, we're working in an erased world. Well, we have functions which are already erased. They work over objects. Well, when you'll be extracting this element here from an array, you'll need to box it to be able to generically work over all kinds of elements of collections that there could be. And so we're introducing boxing that wasn't there in Java. We're also having the operation being passed as a lambda. Compiler doesn't know and VM doesn't know what kind of operation is it anymore, so we'll have a dynamic dispatch here. We'll have the predicate check, because the reduce doesn't have the starting element, the 0 element. We didn't initialize the accumulator as we did in Java explicitly. So we'll have one more branch per every iteration here. And we'll have one more dispatch, because the reduce itself also doesn't know what kind of reduction operation does it do. And then finally, you're going to do addition inside the SOP apply. But when you'll do addition, you'll need to return it once again to arbitrary location, which doesn't know that it works in primitives. So you'll box it once again. And then finally, you'll do index increment. So you're doing a lot more stuff than Java was doing. This is the cost of you being generic and being able to abstract over all the things. And just to give you a small baseline to know how much does this stuff cost, single boxing or single allocation costs on average as much as 5 dynamic dispatches. And by dynamic dispatches, I mean the dispatches which happen to be megamorphic, where there are multiple targets where they can dispatch to. Every dynamic dispatch is more or less equivalent to 3 static dispatches, where there is either you're calling a static method or a private method, or there is only a single method that reaches this call site in runtime. And all of this costs more than additions. So all the things that Scala introduced actually cost a lot more than the operations we've been performing. I'm kind of looking at the worst case example here, to be honest, but the same thing happened on a smaller scale in all the Scala code. So the reason why these inefficiencies are there are actually good things, because Scala is built to help you be productive. It allows library authors to build awesome libraries which developers can use in a way which allows them to write small amount of code, which allows them to reach their goal fast. They do it by having higher order types, which includes allow us to have Scala Z, shapeless, and all the funny stuff in type level world. We have generic methods like Java has. We have generic classes. We have multiple inheritance. You may argue that Java has it, but it doesn't have multiple inheritance of fields. So we have pattern matching. We have lazy evaluation. We have garbage collection. We have all the features which make you happy. Unfortunately, if we consider all these features, JVM doesn't have any of them. All of these features make JVM not happy. These features don't exist in runtime. It means that when compiler compiles the code, it needs to express these features in the language which Hotspot understands. And in this case, it means compiling them in a very conservative way. Because as we introduce them in order to allow you to express more stuff, we can't assume that you're going to express only a subset of things that you could have done. You could do all the crazy stuff, all the scary stuff, and because of this, we need to do it in the most conservative way possible to make your application run correctly. And because of this conservative lowering, Scala is slower. So here, we went for the way to make you efficient, to make the programmer be more efficient in writing their code, because we have assumptions that servers are easier to buy than programmers. But if you are actually performance-oriented, if you need high performance, decisions that we took initially can slow you down. To illustrate this on a small example, let's consider a function which does just addition of 2 things. And it doesn't know yet what kind of things does it add. So because it doesn't know what kind of things does it add, it needs a numeric, which will actually define how are these things added. When compiler compiles it, because it doesn't know anything about the t's here, the t can be integer, the t can be double, the t can be float, the t can be complex. It needs to go to the most conservative type possible, and the only common type here is object. This is an example of boxing, which is the slowest thing that I showed you in comparison of performance. So when you +1 here, in order for these ones to actually reach the body of plus, they need to be boxed. And the return type, similarly, will be an object. So if you're going to use it in a decent way, you're going to unbox it. So in this case, you can actually spend a lot more time preparing to call the function than actually doing the work that you asked for. So Scala and Java here went with the approach that all the generics are compiled in the same way. You're doing one conservative compilation of all the code that you have, but some languages, like C++, went the other way. They started doing clones of the methods. They started doing clones of the classes, which are compiled different way. So let's consider a different option, this hypothetical option. What if compiler did it the other way? And it did multiple pluses. So we have 1 plus for ints, we have 1 plus for longs, we have 1 plus for doubles. Now we can call plus for ints efficiently. We don't need to box it anymore, but we'll have a different problem. Scala has 9 primitive types. We have 5 types for integer types. We have floats, doubles, booleans, and voids. We also have an object type, reference type. And it means that if we'll do specialization, if we won't do it for complex types, it means you'll have to specialize and generate different versions for 10 types. In case you have a class with n type parameters, you'll need to specialize every of those n type parameters for every type that you're considering. Unfortunately, it means that you'll have exponential explosion of how much code you generate. It becomes even worse if you have generic methods and generic classes, because then you'll have number of arguments. The types that you need to specialize for will be both types of the class and types of the method itself. So you'll be exponential over the sum of number of type arguments. It means that for decent classes, like functions, like function 3, function 4 takes 4 arguments and returns 1 type. It has 5 type parameters. Specializing it and generating all the code will be bigger than the whole standard library and whole akka library together. So in order to solve this problem, 6 years ago, Yulia and Dragos decided to ask user that the idea that he tried, that you maybe not need all the specializations. For example, I don't think that a lot of you are using functions which take 4 voids and return a void. Neither are you likely to use functions which take 7 characters and return a void or a boolean. So in order to do it, to decide what functions make sense to specialize or not, you then ask the user. So he introduced a specialized annotation which allowed you to mark type arguments which you believe are crucial for performance and to say what types to specialize them for. Because this was the first implementation of a prototype, it has some limitations. One limitation is it doesn't support inheritance. If you inherit a class which has specializations, the inherited versions are not specialized. The other limitation is that if you have fields in your class, fields will be duplicated. You'll have both specialized and non-specialized fields. So you'll get a hit in terms of memory layout. Well, the years passed, and we had one more student in Martin's lab, Vlad Uheke, who've been trying to improve over it by introducing the mini box annotation. He understood that all the primitive types can actually be encoded. You don't need to encode all the primitive types separately. Ints can be represented by longs, as well as shorts can. Floats can be represented by doubles. So he changed the encoding to, instead of having 10 to the power of n, have 3 to the power of n. And by doing that, it became practical to specialize types like function 4. Unfortunately, because he needed to dispatch on what kind of type do you actually have and see it in runtime, it introduced slow but sometimes visible performance degradation, in particular for operations like list reversal. It was a more complicated encoding, so it did handle inheritance, but because it tried to be generic over all the kinds of primitives, it had problems with arrays. So because specialization knew that, let's say, t is int, if you have an array of t, well, that's an array of int. In runtime, it is. Unlike this in mini-boxing, because it collapses shorts, ints, and longs when it has an array of one of these types. It doesn't actually statically know what kind of array does it have. And all arrays in Java are different. So it had substantial slowdowns and complications when you used arrays. And it had a very complicated implementation to actually handle all of this. And that's one of the main reasons why it remained plugin for a long time. Vlad did a huge amount of work to make this plugin stable, and now I advise you to use it because it actually achieves what it was intending to, but it was a really long way to get it done. But I want to try and show you one disadvantage of the both approaches when I started. It became apparent to me when I started working on it. So I've been working on collections, as I said. And I've been working on collections which are supposed to be used by all the people in Scala community. When I was working for a collection, I needed to decide how would if I would to use specialized or mini-box, I was to decide what type parameters to specialize and what to specialize them for. I needed to make decisions for you. I needed to find the one size that will fill all of the Scala community. And by doing this, I believe I'll break modularity, because my internal decisions would leak to the properties of your software. Depending on whether you will use a library in the way which I kind of blast, performance of you will either be good or will suffer a lot. So I tried to see if there are other options. So if we'll go back to the same question, so we have function 3. Specialization was trying, and specialization and miniboxing were trying to answer the simple question: how many specializations are needed? In case of specialization, it was 10,000. In case of miniboxing, it was 81. I believe that this is the wrong question to answer. It doesn't matter how many specializations are needed for whole Scala community, because, I mean, how many specializations are needed is a question to ask about when you're asking about specific code. I'm building a compiler. It's likely that my compiler is not similar to the code that you're writing during your day job. I'm working on types which you don't normally work on. If somebody is building a numeric application, he's likely to work on doubles all the time. If you're building a bank application, you're likely to work on big integers or big decimals. So I believe that the first question that we should ask is how many specialization is needed in every particular code base. Actually, this question is also imprecise. So the right question that I ended up answering is how many specializations are needed in every particular code base, including all the libraries that it depends on. So, I mean, all of you are building some application, but there's a lot of more code that you reuse. You reuse at the very least standard library. You may also be using Shapeless, Scala Z, and all these libraries are complicated. And I'm not asking you to know how do they work and answer this in your code base. So, and this built a design for auto-specialization in Dotty Linker. It takes your program, it takes all the libraries that you depend on, it analyzes how do you use them, what will be the types that your particular instance, your particular application would need, and it will only generate the types that you need. If you are actually an interesting guy who uses function 5 of unit, you'll get it. But everybody else won't suffer because he won't need to prepare for you getting it. And the good thing that I like most is that library authors who build the libraries now don't need to think and don't need to do user studies. I don't need to discourage usage of some particular types by not specializing them. They don't need to do hard decisions. They now can concentrate on, once again, building libraries which are convenient to use. So actually, there is a funny implementation artifact that was discovered quite late, but it was awesome. So type arguments and term arguments, like normal arguments that you pass to methods, in the implementation and the analysis are treated in the very, very same way. There is no distinction between types and terms. Well, there's not much distinction between types and terms in Dotty for this particular use case. And if specialization for type arguments means removing of boxing, when you specialize for term arguments, you remove virtual dispatch. And that's awesome. I'll show a benchmark later which proves it's awesome. Okay, and the benchmark has to do with this symbol. This symbol is the symbol of Scala native. We'll have one new backend. We already have one new backend who Dennis Shabalin is working on. He'll give a presentation a bit later about it. And the idea here is, instead of compiling to Java bytecode, to compile to native code. There are multiple optimizations which are done by Java VM for us, which are good, like devirtualization, like type profiling. Unfortunately, because LLVM is not built for languages which abuse those features, it doesn't optimize them much. It means we'll need some other optimizer to do it for us. And yeah, here are the benchmarks that I promised you. So the same code, which just takes an array of integers and computes the average value over it. If you write it in Java, it takes 45 milliseconds. If you write it as Scala 2.11, it takes 900 milliseconds. Lucas has been doing a really good job in optimizing to 12. So he improved the running time by doing some local optimizations here, and it did improve. The previous projects that I used to work on, Scala Blitz, actually outperforms Java here by using some very low-level tricks. And it actually is entirely memory bound. So the 42 milliseconds here is amount of time that it actually takes for you to read this array. It can't get any faster. If you use my current approach in Linker, it takes 68 milliseconds. There are still some abstractions that are left there, which are not eliminated, but I believe it's pretty good. So if you take Scala.js, I believe that Sebastian was able to get impressive results on such a slow runtime, which boxes everything, which assumes that you can do all scary stuff, and I'm quite impressed that it's as good as it looks now. So, and the last thing, that's the one that has to do with Scala Native. If you optimize it with native linker, this particular code, then the phases which come from LLVM itself are able to partially evaluate it away. So So we spent all this morning with Dennis trying to actually not make it partially evaluated away to get numbers. And so Scala Native currently doesn't have threading model. We needed to modify the intermediate representation by hand to say that the fields which are used as accumulators are volatile and they can be potentially changed by other threads. And then we got the numbers which are Scala Blitz-like. Yeah, so it was quite impressive by using all the virtualization and stuff that it allowed us to all perform everything. And so the other question that you may be interested, well, that's an optimizer. As I said, it analyzes all of your program, it analyzes all of your libraries, and it rebuilds it for you. It may take a long time. So in this particular case, well, compilation in Java is really fast. Java is a simple language. They don't do any complicated language feature. Scala is slower. The new Scala compiler is faster. And if you take Scala Blitz, which is actually based on Scala 2.11, which is macro library, so it spends quite a lot of time inside the recursive macros that it defines. The linker in this particular case is somewhere in between Scala Blitz and Scala 2.11. Actually, Dotty in this case is faster than Scala 2.11. It's somewhere around 200 milliseconds. So linker introduces like half of 1.5x of speed up in this particular case. So there are limitations of this approach, obviously. It slows down compilation, as I said, because you're not longer compiling your application. You're kind of recompiling all the parts of libraries that you use. You're not going to recompile parts of libraries that you don't use. But if you touch something, if you use lists, the list will be recompiled just for you with the optimizations which are appropriate for your particular use cases of those lists. In order to be able to do it, I need to be able to read the sources of the lists. And that's where Tasty comes in. Tasty is a project which initially was developed in Scala Meta, where they tried to build the intermediate format for metaprogramming. And now it resulted in the Dotty always emitting it as its own serialization format. So this approach, the auto-specialization, doesn't help if library does tricks. And by tricks, I mean funny casts which assume boxing, for example, which will be unsound if I remove boxing. So let's say if you use the same array to store as absence of element by using null. If I'll specialize this array to be array of primitive, you can't store null there anymore, and your algorithm will break. So my analysis is smart enough to see that you're casting a null into integer in this particular case, and it won't perform optimizations. So starting now, if you want to take most advantage on Dotty and Scala Native, it's better to write libraries which don't do dirty tricks, because you're trying to be smarter than the optimizer is. And one more example is if you have a typed API, but your internals are entirely untyped. I've seen several libraries do this if they are using shapeless to create their API. They want to create complicated types which help the users, but they don't want to mess with those types internally because it's too complicated, you know. And then they just cast everything to any and cast back when they return. Because the internals of the library are untyped, none of these optimizations apply anymore, and they won't benefit at all from them. So, okay, now when we're done with the libraries, the question is about the user's code. When I was optimizing this example, the reason why Scala Blitz was faster, because Scala Blitz knew what is the reuse. The actual reason is this if, which only applies on the first iteration. Scala Blitz knew that if you're doing this particular kind of reduce, it can do the first iteration aside, so that only if will trigger only in the first iteration, but do all the following ones without the if. And in order to do it, I'll need to introduce one more kind of optimization that will actually help all of us. So consider this code. I like this code. That's the code that I normally write. But when I review this code, I spot a problem. The x.size here, when called on the list, takes linear time. And what I'm actually trying to see, if I'm trying to see if the list is empty, I don't need to get the actual size of the list to do it. I'd better write the code on the right. But when I'm thinking, when I'm building an algorithm, when I'm building the complicated program, I don't want to think about such small details. Compiler can do this for me. And in this particular case, it can be actually a lot more severe. So if you compare those two examples written in Spark, that's actually an example from their main page. That's a word count example. The example that they introduce is example on the right. Unfortunately, compared to example on the left, it's somewhere like 70 times slower. The main reason here is this map, which is global, and then you need to do global reduction here. If you instead write it this way, it will be harder to maintain. It will be harder to understand what it does, but it will be substantially faster. When developing libraries and when developing an application, I see this problem all the time. When I write the code, I need to decide whether I will write it fast or I'll write it maintainable. And if I decide to write it fast, everybody in my project will have a problem of trying to understand what it does. This code may be deleted in future and rewritten because nobody was capable of understanding how did it work. Even worse if it had a bug. If you write the maintainable code, it may stay there forever. Everybody will understand it, but you'll be slow and nobody will know that somewhere deep in your program there is this part where somebody made a decision, for now I'll write maintainable, but one day I may come back and rewrite it if we'll have a problem with performance. Several years passed, now you have a problem with performance. Nobody remembers. Somewhere deep inside the core, there is this maintainable code which is slow. So I believe that we need library-specific optimizations here. We need optimizations which know what kind of operations are you doing, what are the ways how to combine those operations, and what are the ways to more efficiently do the same things which users do at their everyday life. So in this particular example with the list, I want this code where the x is sequence, any sequence, list, vector, arbitrary sequence, to be replaced by this code. I don't want to compute length if I'm interested if the collection is empty. And I'm introducing rewrite rules here. So what this says is this is an object which contains rules, which will start rewriting your program. And this particular rule says for arbitrary sequence, if you have expression like this, then rewrite it to this. When I was trying to do similar stuff in Scala Blitz to make it combinable, the average length of the macro was 700 lines of code. To be capable of doing this in all the cases, in all the complex situations. Once again, if you're a bank, you may be working a lot of big integers because you're a big bank, you have a lot of money. It doesn't fit in integer anymore. It doesn't fit in long. So if you're working on big integers, when you're dividing big integer on the other integer, if the other integer is a power of 2, you'd prefer to make a shift instead. It's a lot faster. And it actually doesn't allocate as much memory as the other does. So you can write such a rule which tests if you are dividing by a primitive or by a constant, which is an int here, then this rule will apply. And then you rewrite it to a code where you have this constant a, and you're checking how much bits does it have. If it has the 1 bit, it will execute this code, otherwise it will do actual division. So this rule will rewrite code similar to this one. And then partial evaluation in either Dotty or hotspot itself will see that only one of the branches is taken, and will remove the other. Similarly, going back to the example of collections, if you have multiple filters in a row, then every of those will create an intermediate collection. And it may be slow because of this, if the collections are huge or non-local. So I believe that this code is easier to follow and easier to maintain, but it's slower. And I'd prefer to be able to write this code and compile to write the code into this version. This also can be done with a simple rewrite rule, which takes lambdas. There is one more requirement for this rule to be correct. It needs to check if either of lambdas is pure. One of the lambdas needs to be pure. It's fine if both are pure, but if both are side effectual, this rewriting is actually unsafe. Because they can be printing, let's say, the element that they're checking, and if you fuse them, they will print it in a different order. So the is pure here is actually part of the analysis which Linker does, which is not the purity analysis as if author wrote it as pure. It's more of analysis, somebody will be able to see that if it's not pure. Are there any effects which escape? Are there any effects that is observable that they happen? In particular, when you create a list, actually there are side effects inside, which are therefore performance of creation of a list. You don't want to create a list in quadratic time, but this analysis, though it has side effects inside, is able to see that nobody will be able to observe them. It will be able to optimize it. Also, one more thing which can be done here is if somebody misuses the library and there is no good rewrite, let's say you have a parallel collection and somebody does reduce left on it. And he wants it, well, to be fast and to perform a parallel reduce left. Unfortunately, there is no such thing as parallel reduce left. And if you're author of the parallel collections library, I would prefer this use case to be at least a warning, because you're assuming that it will do something, but it doesn't. And yeah, you can define warnings for this. You can also do easy logging. So you know this example from Java, which also applies to Scala, that if you're checking if your login is enabled in a performance-sensitive code, you don't want to pre-create the closure which actually will create the log message. And you have this funny double checking if it's loggable log, and the log inside will check once again if it's loggable. It's one more code pattern which exists there for performance reasons, but it's very unpleasant to spend time thinking about it and writing it and reviewing code which is bigger because somebody wanted to be fast. Here, because these rewrite rules apply anywhere, even if they work on Java, if they work in Java logging, you can define them. So, and similarly, you can define easy debug messages, where you can promote the source into runtime. You can ask the question, how does it work? Actually, it works to the rules similar as macros. And because it kind of makes, Scala Bliss previously was implemented using macros. Now I'm re-implementing the stuff which used to be in Scala Bliss using rewrite rules. And I want to give you some guidelines when to use one or another. So in particular, the rewrite rules can be defined everywhere in the library, in the program or in the library. So if you want to define some rules which should be separate, you still have the default implementation which implements virtual calls and stuff, and which are simple. Maybe rewrite rules are better. Macros, unlike this, are a very wonderful feature to define new language expressions to enhance your language. Rewrites rule happen after typer that don't participate in typing at all. The application in rewrite rules in this case is based on the analysis. They will apply even if you have virtual calls, which happen that they actually dispatch to places which are optimizable. Unlike this, macros can only work if you syntactically call them. Because macros can only be defined inside Scala classes, you can't make them work for Java classes without magic. Unlike this, rewrite rules perfectly work on Java methods. And they work across libraries. So let's say you want optimization, which is optimization of usage of Scala standard collections inside Spark. Who should maintain and define these optimizations? Is it standard library? Is it Spark? Here, the rewrite rules can be anywhere. They can be in the third library, which is developed by other people. You can have optimization as a library here. Unlike this, macros, they introduce a lot more tight coupling between each other. They are a lot more powerful. Macros can do more because they influence typing. And that's, I believe, the best distinction rule. If you're interested in simple declarative rules, which are there for performance, for improving user experience, but not introducing new language features, you may consider this. If you're trying to do something complicated, if you're trying to, let's say, play with a new language feature that you may then propose for upstream Scala, you'd better go with macros. And it will also help you to understand the internals of compiler. So yeah, I was trying to help you with choosing between meta and macros, meta and rewrite rules. Actually, you don't have to choose. You can use meta inside the rewrite rules. Then you'll have a more complicated case when the meta will trigger. Let's say if you want to actually do complicated stuff. Actually, this will be really slow. But this allows you to bring back expressivity that you had with meta. So you don't have to choose, you can combine them. And by the time I showed you all this rewriting rules, which can come from any library on your class path, you should be scared. They can break everything. They can replace all the truths in your program by false. So from the start, I want this to be integrated with testing. Every time you define a rule, every rule is a test to be checked by in Scala check in particular. If you define a function that you take as an argument, I'll be synthesizing side-effecting functions to make your rule break, unless you ask for these functions to be side-effect free. And this is the only way how you will be able to define such a rule. This test suite will make a stamp on a rule which says that this rule is applicable. This will be checked. Of course, somebody can forge the stamp if he wants to, but for me, it makes me sure that during my day-to-day life, when I be optimizing collections in particular, I won't not knowingly define the wrong rule just suddenly. Okay, so the current status of all of this tests is prototype, unstable, even more prototype than Dotty. But as similarly to Dotty, if you're experimenter and you want to participate in evolution of the language, that's the best moment for you to join us in our effort to build better Scala. We're still flexible enough to consider ideas. We still didn't start stabilizing ourselves. When we will start stabilizing ourselves, we'll be less interested to consider complicated ideas which can stop us from stabilizing the code base. Speaking of the code base, so I believe that while I specialize stuff, I'm creating huge amount of default methods, which nobody ever created in a single code base. If you try to specialize list flat map, you have 20% probability of hotspot to segfault. And it's segfaults inside C2. Yeah, and server compiler. So I'm still trying to understand who's wrong here, but because it has huge probability of succeeding, and I literally mean it's seg false. It doesn't throw an exception or something. I assume that they actually have a bug, but it's quite hard to debug. So speaking of the implementation, once again, implementation is simple. If you compare it with specialized or mini-boxed in Scala C, the most complicated part, which is analysis, is smaller. The specialization part is a bit, if you add it to analysis, it's around of the same size as specialization. But actually, I'm a lot more confident that it's right. And the main reason is because previous specialization used to work on trees. This one works on types. And if you work on types, there is a lot of check-in infrastructure in Dotty, which will make sure that you use types correctly. We have quite an impressive type system in Scala, and in Dotty we use its advantages to make sure that we're building the correct compiler. We're retype checking the program after every phase to make sure that we didn't break it. And because specialization creates very complicated types, if they are correct, it's a very strong indication that the transformation is correct here. As I said about using tricks, some collections don't benefit, like vector, because vector stores nulls inside arrays, which presumably are used to store integers. Most other collections, like list arrays, list buffers, they work perfectly. You get the best performance possible here. And it's open source. It's on GitHub. Yeah, it's awesome. So I want to thank everybody who helped me to be where I am now. That's Julian Dragos, who started with specialization, and he built a system which was complicated, and we understood that are problems there to be addressed. And Vlad Ureke tried to address these problems by building even more complicated system, and he succeeded in doing this. Now, if you have performance-sensitive code, and you have problems with primitives today in production, I'll advise you to try mini-boxing. It has been stabilizing for 3 years, and it's pretty stable now. So I want to thank Eugene Burmako, because while working on Scala Meta and Scala macros before this, he came up with this idea of tasty, and he convinced, in particular, Martin to have it in Dotty. I want to thank Andrei Lotak, who helped me to build the static analysis which is needed here. And of course, nothing of this would have been possible without Martin. He was supervising all of us, and he made this awesome language, which I love. Okay, thank you for listening to me. And we have precisely 5 minutes for your questions. Yes, please.
Hello. You've mentioned that Linker would work only with libraries which have tasty data in them.
Yeah.
But you also mentioned that rewrite rules also work on Java code. How does that combine together?
So rewriting rules will work on the Scala code which uses Java code. So if you use methods defined in Java and you optimize your usage of them, you can use rewrite rules to do this. Rewrite rules won't apply to Java standard library. So one more detail about the tasty here. So what Linker actually creates, it creates a single jar. It's like a smarter ProGuard, which uses the advantages of Scala type system. But it attaches the correct tasty to it. So if you're building something optimized and somebody needs to re-optimize with different assumptions, he can perfectly depend on you. He will just do it once again. Yeah, thank you.
Thank you.
Yes, please.
Okay, try to speak loud enough.
Okay, I'll repeat.
So, this kind of goes in one way that you try to use the primitives internally and don't have to talk about, but in the way you are kind of encouraged to use primitives more. And as an application developer, I see a problem with that because you have this tacit overflow where you come modulo some power of 2, sorry.
Mm-hmm.
And I think we should get away from worrying about this and go more towards using big integers for application code.
Okay, so the question was that all of this presentation was optimized for usage of primitives. And maybe we should consider some more complicated classes like bigins. So I've showed you the basis of optimizations. There are other optimizations which rely on those. So in particular, if you were to write bigint in Scala, because internally it uses primitives, then there are a lot more optimizations which will fire later, either by hotspot or by my phases. In particular, I'm inlining objects which don't escape scopes. So if you do pattern matching, the tuples won't be allocated. If you have fields which are case classes and they don't escape the class, they will be split into fields, just object fusion. And it seems that LLVM is doing quite impressive stuff here, because it was just able to eliminate everything and just get a single constant out of it. And the constant was correct, by the way. Yeah, thank you for awesome question. Yes, please.
Hi, so about the rewriting rules,
Yeah.
do you do several passes? Because clearly the rules are not idempotent, so they can influence each other. Like the filter example you showed for two chained filter calls. If you chain 4 filter calls, then it could apply 3 times, and then it would simplify the whole filter chain.
Yep.
So do you do passes until the code stops changing, and if so, isn't that slow as hell?
So the way it works is it doesn't actually try to find the code pattern that you wrote. It builds the call graph for it, and it sees if there is a similar call graph which works as a really fast index. The call graph will be rebuilt when the transformation will be done, and it will be rebuilt incrementally. It will start losing precision by doing this, but the assumption is that specialization has already happened, and the precision of the call graph is not that important anymore, and that the rules that you're defining are very important. You're having big savings here. So also speaking about the rules, some of the details, currently the rules I ordered by the size of the tree that they match on, with the assumption that the big rules are matching on more complicated cases which are more rare, and that's why they introduce more performance improvements. Currently, there is no plan to introduce priorities between the rules, because I want to keep the system simple. I haven't yet seen an example where the priorities matter. I'd be glad if you have one. Thank you. Yes, please.
So when you specialize, you are actually specializing on primitive types. But you're always specializing on primitive types. Sooner or later, the JVM is going to have value types for more complex types. So when you start specializing on those which I assume you would want to do, you get something which is very, very similar to non-erased generics. So does this change the semantics of Scala? Is something that it is worth considering for Scala altogether?
Okay. So the question was that, because here I presented a system which specializes for primitive types, it would make sense to specialize for non-primitive types, in particular the value types which can come as part of, for example, Project Valhalla. So I'm presented the simplified system. In practice, I actually have a bound on how much your program can become bigger. Currently, this bound is 0.7. So your program can become 0.7 times bigger, which means smaller. And I'll start duplicating classes for non-primitives if I still have a budget to do it currently, with assumption that if I'll duplicate lists for tuples, for example, and this tuple doesn't escape, then I can inline the tuple and allow more optimizations to happen. This approach is quite flexible, and I'm not in any way tied to specialization for primitives. If Valhalla will be delivered and will have something great for us to offer, we'll of course take use of it. Thank you for an awesome question. Yes, please.
So first of all, I think the rewrite rules for libraries, that's a very good idea. But how does it compare to the rewrite system in LMS and Scala?
Okay. So the main difference between these rewriting rules is that they support virtual calls. And you can define rewrite rules which work on standard Scala libraries, on Java libraries and stuff. These rewrite rules, the design is heavily influenced by both LMS and Haskell rewrite rules. But they try to take advantage of, well, and be like Scala. They try to use advantages of our type system. They try to use advantages of implicits. And I believe they fit better in the design of Scala language. Both in terms of when do they apply, both in terms of how to ship them and how to write them. Thank you for asking the question.
Hi. Do you have any idea of how this will affect debugging when you modify the call, the call graph?
So the main reason why tests are there is to make sure that you don't have to debug the optimized code unless you really have to. After all these optimizations, the code has nothing to do with what you wrote. The fields aren't there, the classes are not there, the methods are not there. If the stuff is pure, it can reorder it and compute it in a different order. So debuggability here currently is not more or less supported. The assumption is that because we have quite a complex checking system, that if your program runs correctly before the optimization, it should run correctly after the optimization. And if it doesn't, you can easily enable all the self-checking system inside its optimizations, which will explode if they did something wrong. And then you'll report the issue to us. Thank you. Okay, thank you, and see you around.